So what we're doing today is the beginning of what's called differential equations. And differential equations are just equations that involve a derivative. So any equation that has a derivative in it that you need to solve is called a differential equation. Differential equations can have what we call a different order to them. They have maybe a first order, a second order, or a seventh order differential equation. The order of the differential equation just involves whatever the highest derivative in that equation is. So this differential equation right here, which is a differential equation because it has a derivative equals something, and we're going to be solving it eventually. This is called a first order differential equation because the largest derivative in it is a first derivative. A second order differential equation would just be like this. So, well, that's one number is supposed to be a 2. This would now be a second order differential equation. Or I might even have something added in over here like this. This is more complicated than what we're going to get to in this class, but this is also a differential equation. It's a second order differential equation. And, there's ways to go about solving something like this, but we won't deal with it in this class. This is just called a first order differential equation. And to solve a differential equation just means to find all the functions that satisfy this equation. Just like when you solve for x, right, in an equation like 2x plus 5 equals 7, solving for x means solve for x, okay? Right? You get x by itself and you find all of the things that make all the x values that make this true. So 1, right? Here it means find all of the functions that make this true. So to figure out all the functions that make this true, we have to anti-differentiate both sides of this. And we'll bring this dx over here and then just anti-differentiate. And it's pretty straightforward. What's the integral of dy? What's the integral of dy? Will this help? What's the integral of 1 dy? Which is what dy is. It's 1 dy. Everybody's audio must not be working because you should all be very quickly and easily responding to that. What's the integral of 1 dy?
Is it 1/2 dy squared?
No.
Is it just 1?
Y?
It's just y, right? The integral of 1 dx is just x, right? Or the integral of 5 dx is 5x. Well, the integral of 1 dy is y. So this is y, and this is what? What's the integral of secant squared x plus 2x plus 5? Integral of secant squared is tangent x. Integral of 2x is
x cubed. No, sorry.
X squared.
X squared. Yeah.
squared, and the integral of 5 is
5x.
5x. And anytime we integrate something like this, we have to add in a constant, right? Technically, there's a constant on this side too, but a constant on this side and a constant on this side, well, I can subtract one constant from the other, and it's just some constant on either side I want it to be in. Okay. This right here, which was literally just us integrating our original function, our original differential equation, is what we call the general solution to this differential equation. It represents every single possible function that could have secant squared x plus 2x plus 5 as its derivative. That's it. That's a general solution to a differential equation. It's just what we've been doing before. What we're going to do, though, is we're going to add something to this. We're going to change this a little bit so that rather than finding a general solution with this plus c, where there's an infinite number of different equations like plus 1 and plus 7 and minus 35 and plus 0 that all still give you this as the derivative, we're going to add in some initial conditions to say, all right, well, when I solve this differential equation, I want y to be 17 when x is 3, for example. And so we'll have to then plug in those values into your general solution to find the constant to get the specific solution, or we call it a particular solution to that differential equation. So that's what everybody good with what we've just done?
Yep.
All right, so now we will add in this initial condition here. So when we add in the initial conditions, what we usually call these are initial value problems. And each initial value problem have just one particular solution or one unique solution to it. And so we want to know the function that has e to the x minus 6x squared as its first derivative that also goes through the point 1, 0. So the first thing we need to do is just throw that dx over there and say this is dy equals e to the x minus 6x squared dx, and then integrate. And what's the integral of dy?
Y.
Y. All right. And what's the integral of e to the x?
E to the x.
And what's the integral of minus 6x squared?
2x cubed.
Yeah, minus 2x cubed. And we should attach a constant. There could be a constant on this side and a constant on this side, but I'll just throw one constant onto one side because it's the same thing, right? If this has a constant and this has a constant, it's just like having one constant somewhere. What's next? We want it to have to go through this point, the point 1, 0.
Plug in our x and y and find c.
Exactly. So we'll plug in x or 1 for x and 0 for y. 0 equals e to the first power minus 2 times 1 to the third power plus c. And this is just e minus 2 plus c equals 0. So what does our constant equal?
It's a 2 minus e.
Yep, just comes out to be 2 minus e. Good. So our final function here, that is the solution, the particular solution to this differential equation, is just y equals e to the x minus 2x cubed plus 2 minus e. So we'll note that if we were to take the derivative of this, we get e to the x minus 6x squared, and then the plus 2 and the minus e would go away. And if we plug in 1 for x, we will end up getting 0 for y. Everybody good there?
Good.
All right, let's do another one. Let's find the particular solution to dy dx equals sine x plus 2x. And we want to have a y-intercept of 3. So what point, what coordinates is that telling us? Needs to be x equals
0, 3.
0 and y equals 3. 0, 3. Exactly. Good. So we'll bring the dx over and we'll integrate both sides, which will give us what? On the left-hand side.
Plus x squared.
Yeah, sorry, what did you say?
Oh, y equals negative cosine x plus x squared.
Good. Negative cosine x plus x squared. And then don't forget plus c,
Plus c.
right? And that's what we're going to figure out is what that c value is. So in order to do that, we'll plug in 0 for x and 3 for y. Negative cosine 0 plus 0 squared plus c. And what's the cosine of 0?
1.
Yep, so we got 3 equals negative 1 plus c, or c equals
4.
4.
Good. And so our final answer here will just be y equals negative cosine x plus x squared plus 4. And that has a y-intercept of 3. And if you take the derivative of negative cosine x, you get sine x, and you take the derivative of x squared, you get 2x, and you take the derivative of 4, and it's gone. And this is our particular solution to that differential equation. Good or no?
Good.
Can you leave that up for a tiny bit?
Yep. So hopefully you're noting this is not really all that much more difficult so far than what we've been doing with our integration. The only thing is we got one extra little step at the end where we plug in these points and do a little bit of algebra, right? You know, back to your like algebra that you learned in 4th grade or something.
All right, thank you.
Yep, no problem. Any questions so far? No? All right. You guys want to try and do this one on your own?
Sure.
All right. Perfect. Ready, go. I'll give you 2 or 3 minutes here. Probably won't take you more than 2 minutes. Ready, go. Together and see what we got. So first you brought the dx over and integrated, which would give you y equals what?
X squared over 2 minus tangent x plus c.
X squared over 2 minus tangent x plus c. And then we said when y is 3, x is 0. 0 squared over 2 is 0, right? Minus tangent 0 plus c. So what's your constant?
3.
3. And so, well, that's not a good looking 3. Let's try that again. So our final answer then that you came up with was y equals x squared over 2 minus tangent x plus 3. Is that right?
Yes.
And you felt really good about yourself until right now when I said that this is not quite exactly right. Now we've done nothing wrong, but we're missing something here that you wouldn't have known about because we haven't talked about it yet. So I want to go back to this first particular solution that we talked about first here. So e to the x minus 6x squared, we integrated it and got this cool looking function e to the x minus 2x cubed plus 2 minus e, right? I'm going to graph that. It was e to the x, what was it, minus 2x cubed plus 2 minus e. Does that sound right?
Yeah.
Okay. I got to zoom out a little bit just so we can, oh, that's not out, that's in. If we zoom back out, we can see, you know, it just is this nice smooth curve. It's kind of got some weird point of inflection stuff and local maxima minima stuff going on here, right? And it drops way down here, hits a local min, goes up, goes off towards infinity, goes off towards infinity to the left, right? Just I mean, you know, maybe not a function you knew what it looked like, but a pretty straightforward function. Everyone would agree? Would you guys all agree that's a fairly straightforward function? Nothing too crazy or special about it?
Yeah.
Yeah.
Oh, good. All right. Even if you don't agree, just lie and tell me that you do. What about the next one that we did after that? What was that function? I think
Y equals negative cosine x plus x squared plus 4.
negative cosine x plus x squared plus 4.
Yeah.
All right, cool. So there it is. Got a local minimum. I mean, it pretty much just looks like a parabola, sort of. Yeah. Nothing too weird about that, right? Pretty normal, run-of-the-mill, average-looking function. True?
True.
Okay, cool. Now let's throw in the one we just got. What did we get?
X squared over 2 minus tan x plus 3.
Tangent x parentheses plus 3. All right, now this one looks a little less normal, doesn't it?
Yeah.
Yeah, clearly, right? Is that, yeah, zoomed out too much, and now it's just a big block of green. What's going on here that's causing all of these like straight lines that aren't actually straight lines but look like straight lines here? What's happening? What's causing all those?
Vertical asymptotes.
Yeah, vertical asymptotes. We've got some we got some vertical asymptotes. In fact, we have an infinite number of vertical asymptotes on this function, right? Every, they occur at pi over 2, right? Every increment of pi over 2 after that, or every increment of pi. So like there's one at x equals pi over 2. If I put in a 3 there, there's one there. There's one 5 pi over 2, 7 pi over 2, 9 pi over 2, negative pi over 2. Negative 3 pi over 2, we got one, negative 5 pi over 2, negative 7 pi over 2. Yeah. Everybody agree with that? Sorry, there's a trash truck going by my house. I don't know. Hopefully you can all still hear me, yeah?
Yes.
All right. I'm just gonna wait for them to go. And away they go, they're gone. All right, great. I guess maybe I shouldn't just leave my front door wide open. Kind of makes things a little louder. But we've got all these vertical asymptotes, right? So anytime that your solution, your particular solution to your differential equation, that's not the right one, this one, has asymptotes, or it has any sort of discontinuities in it, you have to take that into account. And so there's an important thing that we need to know about differential equations, which says that if the particular solution has any discontinuities, the solution is only valid on the continuous interval that contains your initial condition. And this is an important fact that you need to know. Okay. Anytime your particular solution, this is only true about particular solutions, not general solutions like the first one we did. But if the particular solution has any discontinuities, your solution is only valid on the continuous interval that includes your initial condition. So we just said x cannot be, what are we saying? Negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and so on, both directions, right? So where does x equals 0 fall in between two sets of asymptotes, or in between a set of asymptotes? Between which two sets of asymptotes?
Negative pi over 2 and pi over 2.
Yeah, negative pi over 2 and pi over 2. So this is valid on negative pi over 2 to pi over 2. Okay. This is just sort of like a technical thing, right? That we can only say that it must be true on this interval, because I could have this same function with this same derivative, but with like a plus 1,000 between pi over 2 and 3 pi over 2, because that doesn't matter. The derivative is still this. And my function, as long as between negative pi over 2 and pi over 2, it has a plus 3, we'll still go through that point. It doesn't matter what's happening between pi over 2 and 3 pi over 2, or between 3 pi over 2 and 5 pi over 2, or between negative 3 pi over 2 and negative pi over 2. This part of it only must be true between negative pi over 2 and pi over 2 to make the initial condition true. In all the other portions of it, it doesn't matter what that constant is. Does that make sense?
Yes.
Cool. So you'll need to do that with every particular solution. We didn't do it here because no discontinuities. We didn't do it here, no discontinuities. And we didn't do it here, even though there was discontinuities, because this is a general solution, not a particular solution. All right, we got 3 minutes. We're going to do one more. I'm going to give you guys 2 of those 3 minutes to do it on your own. And then we will come back and make sure you got it correct together and make sure you do your interval on which it's valid. So take a minute or 2 to do this one, and then we'll talk about it. Ready to go. So You brought the dt over and you integrated both sides to get a equals what?
ln absolute value of t minus 1 over t plus 6t plus c.
Yeah, minus 1 over t or plus 1 over t?
I got plus
I
one.
got
It should be plus 1 over t because that's a negative t to the negative 2 to start with, right? And so that'll go up to negative t to the negative 1 and we'll divide by a negative 1.
oh, okay, I see.
Good, everybody good with that? Okay, so then we plugged in t equals 1 and a equals 0. And what did you get for your constant?
-7.
Perfect, good. And so you should have got the function a equals natural log absolute value t plus 1 over t plus 6t minus 7. And then you would have noted that what is the only value that t cannot be in this equation?
0.
T cannot be 0. And so that means that the domain of this is negative infinity to 0 and 0 to infinity. But we only pick the one that includes our initial condition. So which one includes our initial condition? Negative infinity to 0 or 0 to infinity?
0 to infinity.
0 to infinity because t equals 1. So we will say this is only valid for 0 to infinity. Good or no?
Good.
Perfect. Any questions on that?
Wait, could t be negative? Because of the
T
natural
could
log?
technically be negative because remember when we do the integration here, it's absolute value of t. So technically we could.
Oh, right.
For t.
Okay, thank you.
If we wanted to, we could, and this is totally not necessary, but because we're going from 0 to infinity and now only saying positive numbers, we could eliminate that absolute value and say it's just natural log of t plus 1 over t plus 6t minus 7 since we're only talking 0 to infinity. But perhaps if we'd had negative infinity to 0 in there, we'd have to keep the absolute value on. But that's another point for sort of for a different day. We're going to talk more about that kind of stuff and tomorrow probably, maybe the day after. Any other questions?